So good morning to all of you, and good morning also to those who are in other places in the world. Good evening, good afternoon. Well, the topic of my presentation will be advancement in ventilation, and I will, in first part, discuss the present state, and then suggest what we can do, and of course there is much more to be done and suggested by other colleagues. So, where do I? Okay. No? All right. The purpose of ventilation is primary is to provide clean air for breathing. And we have to provide this to every person in the room. Not some average person does not exist, not to the room in general. And often we use ventilation air, to condition it in order to achieve better thermal environment in space. But we should not forget the primary aim of ventilation. But what is the goal of ventilation design? The primary goal is to provide healthy, comfortable, work-stimulating environment. And there are several other important goals, such as energy consumption, such as airborne transmission to be reduced, flexibility in space use, and also reduce size and cost of HVAC systems, control and there are several others. So let's go to the basics. Ventilation. The word ventilation comes from the Latin word ventus, which means wind. And we hear every day in weather forecasts about the wind and what they tell us at least about the strength and its direction, because it's related to air movement. In our field of ventilation, we also deal with air that's distributed, but we have simplified very much. When we talk about ventilation, we talk about ventilation rate most of the time. Very seldom. And we talk about air distribution. And this is something we have to change. Because it is not sufficient only to tell how much air we supply. We have to consider where this air goes. And what we want is that to go to each occupant. So air distribution is very important because it defines how the clean air reach the occupant. It defines also reduction of pollution, but also we should remember, and I will stress again later, that it is very important for the spread of the pollution which is generated in spaces. So we have to consider it. And of course it's important for comfort of occupants, draft or similar. And when we design air distribution, we have to consider several important issues. First, that in rooms exist complex interaction of flows, not only ventilation flow. There are buoyancy flows which are generated by occupants, by heated or cold surfaces and objects. And those may change in time, not because only occupants are moving, but also because outdoor conditions may change. Also, it is very important to consider location and of the pollution source and type, of course, of pollution source and occupants' activities. Today, we use mainly total volume air distribution, where it is mixing, displacement, underflow, but mixing is mainly used today. And in this case, diffusers are where we supply the clean air located on the ceiling, which means quite far from the occupied zone where occupants are. We know that building materials pollute. We know that occupants also pollute. And what happens is this air which we supply far from the occupants, from the ceiling, it passes over the surfaces, collects the pollution, and brings it to the occupied zone. So in reality, occupants do not breathe clean air. It is already mixed. So we bring unintentionally the pollution which you generate outside occupied zone and bring it to the occupants. Not fair. There are limited possibilities to improve this situation, limited possibilities to improve inhaled air quality and also to reduce the energy. If we try to increase ventilation, as it is suggested quite often, we can improve the indoor environment, but it will cost energy. And it is also suggested to reduce ventilation rate. But then what we do is that we get energy saving somehow, but a mediocre environment. So there is no win and win situation in this case. And airflow, as I already mentioned in spaces, is quite complex an interaction, and we cannot control it. These two figures show clearly show how outdoor conditions may change the air distribution and then exposure of the occupants. So occupants are all the time exposed to changeable conditions, and airflow interaction is very difficult to be controlled with the present way we do ventilation. Now, during the last years, very many good guidelines were developed to fight against ventilation. And in all these guidelines, increase the ventilation rate is recommended. And already I showed that, yes, this will improve the environment. But also there are studies showing that not always this is the case. The figure shows how air might be distributed, the supply air, and how it will spread the pollution. And in fact, exposure of the doctor and the patient in bed may increase. So it's very important to remember that not only reduction of concentration of viruses, but also we may spread them in a not desirable place. Of course, there are other disadvantages of increasing ventilation rates, such as systems should be expensive and bigger. We may cause discomfort, energy will increase. I'll show you some results on how important is the air distribution, what we do today. In one of our climate chambers or test rooms, air distribution test rooms, we simulated office with two occupants. The one with the black t-shirt is infected and the other one is exposed. And we use breathing thermal mannequins. We can control the breathing mode, the breathing frequency, pulmonary ventilation rate. And what we can measure is the concentration of either particles or tracer gas, which we most often use in the inhaled air. We measure also temperature and humidity in the inhaled air. So we may also assess not only cleanness of the air, but to some extent perception. And we have, as it's shown in the slide, we simulate with different tracer gases pollution, which is generated exhaled air, and different from body bioinfluence and building materials. In this case, it is floor. We evaluate airborne transmission by exposure assessment. And when we use a tracer gas, we can calculate the normalized concentration, which is the concentration of tracer gas in inhaled air minus the concentration of the same tracer gas in the supply air, typically 0 or close to 0, divided by the concentration of the exhaust minus the same concentration of the supply air. And what means that if normalized concentration is 1 or close to 1, so the inhaled air is not clean. And when normalized concentration is close to 0 or 0, it is clean air we inhale. So we protect the occupants by the ventilation. And here are results in some of the total volume ventilation cases. We compare displacement ventilation with underfloor ventilation with a short throw length, as it is shown on this slide, with underfloor ventilation when it is designed with this long throw length, and then mixing ventilation, the red bar. And again, in the room is the same. We have a front occupant who is infected, exhaled air is infected, and the back, the occupant at the back is exposed. And what we can see is that displacement ventilation and underfloor ventilation with short throw length are quite good, very close. Normalized concentration is very close to 0, so air which the exposed person inhales is rather clean. But this is not the case when we use underfloor ventilation with long throw length, and especially in case of mixing ventilation. So the inhaled air is mixed with the exhaled air by the simulated infected occupant. So let's come back to the design of ventilation. That was our goal. But what I showed several examples is that, in fact, it is very difficult to achieve this goal with the present way we do design. And already Lydia showed that paradigm shift is needed. And I will show you in the next several slides how we can do that, according to me. And first, we should go from communal indoor environment to individual indoor environment. And we should go from total volume ventilation or heating and cooling to individual, to advanced heating, cooling, and ventilation. And instead of ventilating as we do today, we supply the air to nobody, in fact. Our aim is to get as much as possible mixing. We should supply at least part of this air locally to each workstation. So the occupant, at the time they are at the workstation, they breathe cleaner air. And that is not very difficult. So the paradigm shift requires that we focus on each occupant, not on the room, and not on the average occupant who do not exist. In order to do proper ventilation design, I think that we should follow principles which are, in fact, quite well known. And the first one is source control. We have to reduce the pollution. By pollution, I think it is heat and contaminants. And then we have to supply heat or coal and clean air where it is needed, as much as it is needed, and only when the time it is needed. And we have to make the air distribution in a way that we can exercise active control, considering the airflow interaction, considering the occupant behavior, density, and so forth. And it is very important that we involve occupants in this process of generating their own microenvironment, because there are huge differences between people. And the easiest way to do this is to focus on occupant-targeted ventilation. And in this case, we use the HVAC system, the air handling system, we use ducting system, but we mainly play with the air distribution in the space. Here are shown some examples on this underfloor ventilation with local distribution of the air. This is localized chill beam, which we have developed in cooperation with Halton. This is another meeting room, how we can distribute the air. This is a patient room in hospital. There is a slot air supply diffuser, and we use deflector simply to discharge the air to the height where the visitors are, so close to their breathing zone, and similarly for the patient in the bed. REHVA is preparing a guidebook on occupant-targeted ventilation. Hopefully it will be ready early next year. But today there will be a workshop on this topic in the afternoon, 4:15, in Rotterdam A, probably it's this room, on occupant-targeted ventilation to be discussed. More advanced air distribution is personalized ventilation, and in fact, in several of guidelines which were developed at this time, the last 2 years, on airborne transmission and COVID-19, personalized ventilation is suggested. And it's very simple. Simply, the part of the air, as already mentioned, is supplied very close from air supply device, which can be controlled by the user, direction, sometimes temperature and humidity. And during the last 25 years, we have studied this system, and we have performed a lot of physical measurements. We have done experiments with more than 3,500 people to ask them how do they feel it. And the results are that we provide clean air for breathing and individual control. People are very happy with that, and they like it. Preferred environment can be achieved. Perceived air quality is favorable, quite good. We have indicated improved health, which means decrease SBS symptoms, eye irritation symptoms, increased productivity and energy savings. Unfortunately, I do not have time to show you more results on this. But now the system is implemented in several buildings in Denmark. This is quite big. Dealer room in one of the banks where 250 dealers, they have each has its own personalized ventilation and can benefit of that. At the beginning, already when we started to study personalized ventilation, it was more than 15 years ago. There was no COVID-19, did not attack at that time, but there were other airborne transmission viruses that can be transmitted through the air. And we tried to compare the personalized ventilation performance with total volume ventilation with regard to airborne transmission. And what we did, we used the reproductive number, which is number of secondary infections that occur in a room where one of the occupants is infected. So we simulated, we did measurements, but also we did calculations for a room, meeting room with 10 persons, and one of these 10 persons is infected, and they work together 8 hours. And we did the calculation for influenza virus because this was available at that time. And we started first to compare the two systems at 10 liters per second per person. And what we got is that at the end of the day, after 8 hours working together, about 7 of the 9 persons who were not infected, they might be infected. In case of, this was with mixing ventilation, in case of we apply personalized ventilation, it was unlikely to be infected, any of the occupants. And then we decided, as it is recommended today, to increase the ventilation rate. We increase it 4 times to 40 liters per second. It's impossible today to be done. But nevertheless, we wanted to see what is the result. Still, at the end of the day, with mixing ventilation, there was a risk that 2 of the occupants will be infected, and unlikely with personalized ventilation. But we have to be careful. It has happened before, and it may happen. Recently, I have read several papers on personalized ventilation. Unfortunately, I have to admit that they were not properly done. And the advices and conclusions were, to my opinion, incorrect. Personalized ventilation will not solve the problem completely. We have to be very, very careful. And I will show you some examples. We have tested personalized ventilation combined with mixing, displacement, underfloor ventilation. I will show you some of the results. The same room with 2 occupants, and the black T-shirt occupant is infected, the white T-shirt is exposed. And we use personalized ventilation as it is shown here. And then what we do is that we look on the normalized concentration, the same what I already explained. We look in the case when none of the occupants use personalized ventilation, a combination of displacement ventilation combined with personalized ventilation. This is the case, and we simulated different pollution, but let us focus on exhaled air, which is the yellow bar. And without personalized ventilation, this is very close, normalized concentration to 0. So the system works. It can protect people from inhaling infected air. And then what we do is that we say, well, this exposed person uses personalized ventilation, and it improves further, almost 0. But human behavior, occupant behavior is different. Sometimes they do not use personalized ventilation. And if it's not properly designed, they may not benefit of it, as it is shown in the example here. The infected person uses its personalized ventilation, gets clean air, but the exposed person does not use personalized ventilation. So as a result, the yellow bar is that the inhaled air concentration of pollution or viruses in inhaled air will be very high. So not always personalized ventilation under all conditions will help. We have to be very careful how to implement it in practice. And this is one of the ways when we combined personalized ventilation with distribution of the air from partition. And we have done experiments with this, and we have done also human subject experiments. It works. It has advantages to be faster than the present total volume ventilation. And now let us move to other premises, hospitals. Hospitals also are ventilated rather much. And this slide shows the hospital bed ventilation localized. It works in the following way. There are 2 boxes. on the two sides of the bed, on the side of the head. In the boxes, we have fans, we have a UV light, HEPA filter. And what happens is that one of the box sucks the room air, might be infected, disinfect this air and clean it from particles. Then it's supplied gently over the patient in the bed so that it discharges the exhaled air toward the box on the opposite side where it is sucked, clean, and discharges air curtain in front of visitor eventually. So this air curtain entrains the exhaled air and move it to the exhaust before it is mixed with the room air. So both the patient but also visitor might be infected. Our result shows that this local bed ventilation combined with background ventilation only at 3 exchanges per hour provides the same exposure as if we try to ventilate the room with background ventilation, but at 12 exchanges per hour, 4 times more. Huge difference. This is a prototype which we have developed, and the air is supplied from this side, exhausted from here. Additionally, we supply clean air and cool air to the occupant. And this is a visualization of we simulate the occupant breathing smoke, and then the jet, which is supplied by this local ventilation, discharges the exhaled air towards exhaust before it is mixed with the surrounding. And we perform human subject experiments, of course not transmission airborne, but just aesthetic and how they feel. And they like it. They do not feel draft, and they report improved inhaled air quality because we supply locally cleaner air. And at the end, now I want to go to another type of ventilation, headset incorporated ventilation. It works rather simple. We have a small box at the belt attached, and in this small box there is a fan UV light and HEPA filter. So we suck the room air, we disinfect it, clean it, and then we supply it up to a nozzle which is incorporated around the microphone. So this air, which is disinfected and cleaned, it's supplied directly to the mouth, to the nose, about 0.3, 0.4 liters per second. So our result shows that we may get up to 90% cleaner air in inhalation. And the second mode of performing of this device is as it is shown here. So it evacuates the exhaled air directly the location of the mouth and nose before it is mixed with the surrounding. And our result shows that we may come up to 80% of the exhaled air to be evacuated. It is clear that in this case, maybe we should consider another background ventilation, not so much to increase the ventilation rate. I will show you now comparison of different methods we use today and may use in the future. This is a room ventilated with normally as today, and with normal ventilation that as it is required, and then increased ventilation. We combine ventilation with air cleaner, and we use this headset in the 2 modes, when it supplies the clean air, but when it removes the exhaled air. And we simulated office with 10 occupants. One of those occupants is infected. They have 2 hours meeting. The infected occupant generates about 2,350 virus-laden particles per exhalation. We assume that the air cleaner is 100% efficient. That's not the case in practice, but for this case, we have this calculation, we have assumed this. And the local headset devices are 80% efficient. And so this is how the concentration of a virus particle, laden particles developed in time in the room. They increase, and of course the highest level is with the lowest ventilation, and the lowest level is we'll come to see with one of these devices. Now let us look in the results. We use an intake fraction, which is the mass intake of infection air to the mass which is generated infected air. So we calculated intake fraction for 2 hours because the meeting was 2 hours. And we calculated in the case as it, for example, class 3 of ventilation, about 48 liters per second, and we got an intake fraction about 0.18. Inhaled air or in occupied zone. And then we increase the ventilation rate to class 1, which is roughly 10 liters per second, but it corresponds, if we put together also the pollution from building materials, about 120 liters per second. And that works, of course. It decreased the intake fraction to 0.08, both inhaled air and in occupied zone. And then we added this local air supply combined with the lowest ventilation. I finish in 1 minute. Local ventilation. So we could, in fact, inhaled air decrease the intake fraction to 0.04, but in the room, still it is very high because exhaled air is not removed by this, any of the devices. It mixes with the room air. And we use the air cleaner. If we use it to generate the same intake fraction, 0.04, it has to supply work with 192 liters per second, quite high. But still, it is quite beneficial because everywhere in the room is low intake fraction. The point is, what shall we do? Whether we should recommend to increase the background ventilation or we just use air cleaners, which is, to my opinion, more practical. And when we use the second mode, try to exhaust the exhaled air, we can get lower intake fraction everywhere and very little, 0.2, 0.3 liters per second per headset. So source control is very important. And this is my last slide, is that I strongly believe that it is need to advancement in ventilation. And what I may suggest is that we should focus on air distribution, and we should focus air distribution for each occupant in the space. And if we do like this, I think that there is a huge work to be done in front of us, but we'll succeed. Thank you very much.